Now that we know how cylindrical coordinates work, let's take a look at how to do integration in cylindrical coordinates. If you remember, when we first learned about doing double integrals in polar coordinates, we learned that the area increment was different than it was in rectangular coordinates. And the same thing happens when we look at volume. So with a triple integral, the volume increment in rectangular coordinates was just dx, dy, dz. But in cylindrical coordinates, we're not looking at a perfect box. We're looking at these cylindrical boxes, which have a top and bottom that are made of polar rectangles, and two of the sides are not flat. They're not flat like a box. So in order to set up our volume increment, we have to think about how to calculate the volume of these cylindrical boxes. And in short, it's the height times the area of the base. We know the area of the base. We did that when we learned about the polar double integrals. We said that area of that polar rectangle was r dr d theta. And so adding in the height differential, we will always use dz, r dr d theta for our volume increment in cylindrical coordinates. So let's set up a triple integral and see how similar they are, integration in cylindrical coordinates versus rectangular. We are integrating the function z times r sine theta. We have our volume increment r dr d theta dz. And we're told that we're integrating over a cylindrical box where r goes from 0 to 2, theta goes from 0 to pi over 2, z goes from 0 to 4. So the first thing we're going to do is copy down our function that we're going to integrate. Copy down that volume differential. And then set up our bounds. Now, the truth is that all of our bounds are between constants, so Fubini's theorem says it doesn't matter which order we integrate in, but since it's already set as r, theta, z, let's go ahead and keep it that way. R goes from 0 to 2. Theta is next. It goes from 0 to pi over 2. And then lastly, we have z, which goes from 0 to 4. So integrating first with respect to r, take note that you have two factors of r in this expression. So if you'd like, you could actually write that as zr squared sine theta, grouping them together. And then that's the only term that involves r, so that's the only thing we're really integrating. The z sine theta carries over like it's a constant. R squared becomes r cubed over 3. And then we evaluate that between r equals 0 and r equals 2. So we'll copy the z sine theta. We have 2 cubed over 3 minus 0 cubed over 3. So that simplifies to be 8/3 z sine theta. So we'll replace that inside integral with its equivalent. So now it reduces it down to a double integral. And we still need to integrate with respect to theta as well as with respect to z. Next, integrating with respect to theta, we notice that theta shows up only once, so we're really just integrating the sine theta. The 8z thirds just copies over like a constant. And the integral of sine theta is negative cosine theta, so I'm going to copy my negative and write cosine theta, and we're going to evaluate that from 0 to pi over 2. So I have negative 8z over 3 cosine pi over 2 minus cosine 0. Cosine at 0 is equal to 1. Cosine at pi over 2 is equal to 0. So we get negative 8z over 3 times negative 1, which is really just 8z over 3. And then we have our last integral that goes from z equals 0 up to z equals 4 of 8z over 3, and we're integrating with respect to z. 8/3 is our constant, we'll factor it out. Z becomes z squared over 2. We're evaluating between 0 and 4. So we've got 8 over 6 z squared, where z goes from 4 to 0. So we really have 8 times 16 over 6. And we've got some reduction we can do here. 6 is really 2 times 3, and 8 is 2 times 4, so I can reduce my 2's, leaving me with 4 times 16, which is 64 over 3 for our final answer. The volume for this triple integral is 64/3. Integrating in cylindrical coordinates is not much different than integrating in rectangular coordinates. Sure, our volume increment is slightly different. It has an extra factor of r in there. But other than that, integration is still integration. The part that you're going to find a little challenging is getting used to the idea of setting up our region when it's given to us in maybe rectangular equations and we have to translate them into polar equations, or maybe the problem is set up already in polar, but we don't recognize what the surfaces are. So being able to translate between them or being able to recognize them in any form is going to be very useful. So let's set up a triple integral. Let's find the volume of the region E, and it's described to be bounded below by a cone, and I have a graph of the cone on the screen. So this is the bottom of our solid. It'll be bounded above by a paraboloid, and we have that on the screen, so this will be the top of our solid. And when we mush those two together, we get the surface that we see on the screen. If we set it up in the order dz, dr, d theta, so that's the order of integration, then we know that the first integral is with respect to z. And for a triple integral, if we're just trying to find volume, we are going to use the surfaces that we're given to define top and bottom. So the bottom bound for z is the cone. The top bound is the paraboloid. And these equations are given to us in terms of x's and y's, but we're not working in terms of x's and y's anymore. We're going to switch over to cylindrical coordinates. So we need to find the equivalent of a cone that's not written in rectangular terms, but cylindrical coordinates. So we'll think back to our equations that translate between cylindrical and rectangular. We'll say, well, I remember that r squared is x squared plus y squared. So I'll replace the inside of this square root with r squared to find that z is the square root of r squared, or rather that z is equal to r. So my bottom bound, the cone, instead of writing it in rectangular coordinates, I'm going to write it in cylindrical, and I'll write z equals r. And then for the paraboloid, we'll do the same thing. We have 2 minus x squared minus y squared. Well, how about we factor out that negative so that it's minus x squared plus y squared? And then we can replace the x squared plus y squared with r squared so that we have the equation of the paraboloid as 2 minus r squared. So that's our first of the three integrals. We do still need to set up our double integral, and that's going to be over the shadow, and the shadow is going to be in the r theta plane. And so the second integral, we need to think about the shadow of this solid. The shadow is projected from where the two surfaces intersect. And so if we project that into the r theta plane, although it looks like it's in the xy plane. Let's call this the r theta plane. We need to think about the values for r and theta that will trace out this shadow. So to find the values for r, remember that we start at the origin and we grow a ray that goes through the region, and then we figure out the values for r. So I can see that as soon as I put my point down at the origin, I'm inside of the region. So r is definitely going to be equal to 0 at its smallest value. And then we need to figure out where the r value is at the outer edge. And to do that, we need to figure out where these two surfaces, the cone and the paraboloid, where they intersect. Remember that we've rewritten them in terms of polar equations. It'll be easier to work with them that way. So the paraboloid, we said, is 2 minus r squared, and the cone is just equal to r. And both of these were solved for z, which means we can set them equal to each other. So we have r equals 2 minus r squared. That will give us this curve of intersection, but projected down into the r theta plane. So this is a quadratic equation. Let's rewrite it as r squared plus r minus 2 equals 0. We can factor this. R plus 2, r minus 1. We've got two values here. R can either be negative 2 or r can be positive 1. Now r equals negative 2 doesn't really make sense in the context of our drawing, so we're going to pick r equals positive 1 as the right value for r. And then we are done with our r bounds. We just need to find theta, and since it is a complete circle, we know theta should be able to go from 0 to 2 pi. So for that second part, we're doing our double integral in the r theta plane. We're going to replace our area increment with r dr d theta, and we're going to replace our double integrals with our bounds, where r gets to go from 0 to 1, and theta gets to go from 0 to 2 pi. So just to set it all up, let's go ahead and bring that inside integral into the integral over the shadow.